Okay, should we get started? Yeah, okay. So it's my great pleasure to introduce Barbara Kaltenbacher, who is Professor of Applied Analysis at the University of Klagenfurt. Barbara did her diploma, PhD, and habilitation in Linz in Austria, and afterwards had several professor positions at various internationally renowned places, such as Göttingen, Linz, Stuttgart, Graz, and now at the University of Klagenfurt. Barbara, in her research, made several substantial contributions to inverse problems, regularization, and constraint optimization, in particular looking at the mathematical analysis and numerical treatment of nonlinear inverse problems. She in particular wrote two seminal books on the topic, one called Iterative Regularization Methods for Nonlinear Ill-Posed Problems, co-authored with Andreas Neubauer and Ottmar Scherzer from 2008, and one on regularization in Banach spaces from 2012, co-authored with Thomas Schuster, Bernd Hoffmann, and Kamil Kazimierz-Skide. Barbara is also very active in mathematical leadership. So at the moment, she is president of the Austrian Mathematical Society, which I believe is coming to an end soon, which I guess you're kind of looking forward to.
No, this is not. This was something else. No, I should not. I will not complain about the Austrian Math Society. It was something
okay.
I was complaining about. Sorry.
Okay, so I really look forward to your presentation, Barbara. The title is Minimization-Based Formulation and Regularization of Inverse Problems, and the stage is yours.
So thank you very much. It was a very kind introduction, too kind at some points, because it was actually the professor positions were a bit too many. Some of them were just temporary. But yes, it's a great pleasure to see all of you again, or at least see part of you again. And it's therefore I would like also to thank the organizers more than usually, because I think in these difficult times it means even more to me and to I think many of us to have this opportunity to communicate. And of course, it's a big honor to be invited to give a talk in this seminar. So it will be about minimization-based formulations. So a topic that some of you might have already heard me talking about. It's of course joint work with some colleagues. So Philipp Hungerländer and Franz Reindl are colleagues at the University of Klagenfurt. K is my PhD student who is working on this topic. And I will also show, if time permits, some pictures from some applications that I have been doing together with someone sharing my second name by chance, and his PhD student. Yes, like this. Okay, I will start off with the kind of usual examples. I will get into examples later on in more detail. So some not exactly these examples, but others will come up later on. In between, there's a section where it's kind of in an abstract setting about these minimization-based formulations and also how to regularize them. I will keep the part about convergence, which is, as usual, a quite technical part, as short as possible, and hope to be able to show you some numerical results in the end. So first of all, just to, in order to have some problems in the back of our minds, the, so to say, typical model problems, ABC here, so coefficient identification in elliptic PDEs. So we might have a diffusion coefficient or a potential or a source term, or maybe all of them, appearing in an elliptic PDE, and they typically will depend on space as does the solution U itself. And they are not known and are supposed to be identified from additional measurements. So one of these examples, namely the C problem, will appear again at the end in the numerical experiments. So also the EIT problem is somehow a subset of this, namely identifying this coefficient A here, the conductivity. But here the stress is on the fact that we only have boundary observations, namely voltage current measurements. And also, usually we only have finitely many in practice. I would also like to mention time-dependent problems because they appear again as a motivation, not in the numerical section, but as a motivation for doing these minimization or all-at-once based regularization methods. So what we want to find here is a parameter, let's call it theta, in an evolution equation, here written as an abstract evolution equation. So this clearly also models PDEs. So if the F also contains a spatial differential operator, it might be a parabolic, or also if it's systems, it might also be a hyperbolic differential operator. And what one typically has are observations at discrete time instances or observations continuously in time. So this should be a U, by the way, sorry. So generally speaking, what we aim for is to identify some parameter, so a coefficient or some initial or boundary condition that is infinite dimensional, so not just single parameters in Rn, but really functions, and they appear in the model. And not only the parameters, of course, appear, but also, more importantly, maybe there appears a state, U, along with the parameter, which is now called Q. So capital A of Q and U is equal to 0 is just, so to say, the general shorthand writing for the model that we are looking at. And in order to be able to recover information on the parameter, we have additional observations. So typically there will be observations of the state only. So sometimes there might be also indirect observations on Q, but the typical setting is that we have some observation of operator C, which is also quite often just a linear operator that maps U into what we can actually observe in this system. So all these spaces are typically function spaces, so usually Hilbert or Banach spaces. And A plays the role of a differential operator. We consider it as mapping into some space W star, so the dual of some space W, which is, so to say, consistent with the usual kind of weak type formulation of elliptic or also parabolic or hyperbolic equations. But it's not necessarily, it's just a, so to say, suggestive notation. And C is the observation operator. So the typical approach that one takes here is to eliminate the model by defining a parameter to state map. So a mapping that takes the parameter Q to the corresponding state U, such that the, by the way, can you see my pointer?
Yes, we can, Barbara.
Okay, thank you for answering. I was not sure whether answering is possible. And okay, and so this mapping S is plugged into the observations. This is what is written down here, and this is how the so-called forward operator, therefore usually called capital F, is defined. So it acts directly on the searched for parameter, and it maps via the solution of the PDE problem into the observations Y. So instead of doing this, alternatively, one could keep this structure of a model and observation equation. So, and therefore also keeping not only Q, but also U as an unknown. And this corresponds to what is often called all-at-once approach. So we consider the model equation and the observation equation as a, so to say, large system, a kind of block system of operator equations, and this is denoted by this boldface F here. And beyond this, one could also go, and this is what I'm going to show you today, and instead of looking at it as a system, to look at it of equations, to look at it as a minimization problem. Before doing that, I would like to motivate why I would like to avoid this parameter to state map, because this is clearly needed in this classical approach in order to define the forward operator. Just to clarify what it is in these examples. So the parameter to state map is the mapping that takes the parameters to the solution. In this case here, it would take these coefficients, or one of them if the others are known, to the solution of the elliptic boundary value problem. Or in the EIT, electric impedance tomography case, it would map the conductivity into the boundary measurements corresponding to all these different impressed currents Ji that are used in order to collect data. Or in the case of this time-dependent model problem, it would be the mapping that takes the parameter theta to the state U that satisfies this initial boundary value problem with this particular theta. In the general setting, so with this model equation A of Q and U equal to 0, the parameter to state map is just implicitly defined by this equation here. So if we plug in S of Q into the model, it should be satisfied. The model equation should be satisfied. Okay, so the first kind of motivation is the fact that if we, for instance, apply some iterative method to solve the inverse problem, then why should we solve the model precisely in each step? So numerically, it might be advantageous to be coarse there at initial iterations of the method. And so this approach of saving numerical effort by avoiding the evaluation of the parameter to state map is one of the motivations, in particular if this parameter to state map itself is a nonlinear map. Also, an example of a motivation appears when well-definedness of the parameter to state map is a problem. And I have put here an example of a so-called singular PDE. Actually, this is something which we worked on together with Christian Claesson a few years ago. You see here a simplified model for a microelectromechanical system. So it's about a membrane that is attracted to a ground plate by an electrostatic forces. So the U here is the state variable corresponds to the displacement of this membrane. Q corresponds to dielectric properties of the membrane, which is sort of the control or the parameter to be identified. And you see here what is expressed by this thing in the denominator is the fact that the position of the ground plate is at -1. So if the displacement is -1, the denominator gets 0, or it gets as large as it can be. And so this term becomes troublesome, so to say. So if I want to define a mapping that takes Q into state U such that this singularity is avoided, we have to be very restrictive about the Q. And the restrictions are really so that they are far beyond what one wants to treat in practical situations. Also, another motivation for this avoiding the parameter to state map is that in time-dependent PDEs, it kind of destroys causality, because in each step of some iterative methods, one has to fully go through all the time instances forward and then again backward to match the parameters. And actually avoiding this parameter to state map can, at least to some extent, avoid these complete going backwards and forwards in time-dependent case PDEs. So this was the motivation for doing this work, basically, and to derive formulations of inverse problems that do not need this parameter to state map. But of course, as you know, for inverse problems, usually one does not only need formulations, one also needs stable formulations, so regularization. And so the first step will be now to, first of all, formulate inverse problems as minimization problems, and then to look at how regularization can be achieved. So let's come back to the slide that I had before about this all at once versus the reduced formulation. So there are these two kinds of formulations here, and both are actually, so to say, special cases of a minimization-based approach. So this is just repeating these two formulations, namely, well, it's quite straightforward, as you all know, that this equation can always be reformulated as a least squares problem. This can be done to the reduced formulation, the classical one here, using the forward operator, but it can, of course, also likewise be done for the all-at-once formulation. So using, for instance, norm, so in the sense of least squares with respect to appropriate norms of both the misfit and the model equation. And here you see minimization is done with respect to Q and U simultaneously. One can also look at constraint minimization problems. So for instance, since the model is the thing that maybe we trust more than the data, because the data is contaminated with noise, let's assume that the model has to be satisfied with equality, and then we only minimize the data misfit under the model as a constraint. And of course, clearly, one can also reverse the roles and say, well, we want to stick to our measurements with equality and then minimize the model misfit. Of course, in reality, one will not do this because of the noisy data. You will see this in a moment. And possibly one will also not put this to zero exactly here, the model. So these are just special cases of many more possibilities of formulating general inverse problems as minimization problems. And there are some very interesting and nice particular examples of formulations of inverse problems. Actually, they exist for quite a long time already, namely these variational formulations. And I think the first problem that has been investigated under such a variational formulation was electrical impedance tomography. So one of the examples on one of the first slides with this seminal paper by Kohn and Vogelius of 1987. And I will actually come back to this variational formulation also for motivating minimization-based formulations. I will also come back to another application example, if time permits, namely identification of sound sources. So now we have formulated the inverse problem as a minimization problem, possibly with constraints. So the cost function depends on Q and U as design variables. So they should be minimizers. And it also possibly depends on the data and also the constraints. So the feasible set here, which is abbreviated by MAD, will usually depend on the data in some way. I will come to more concrete formulations in a moment. So this is so far just a reformulation of the original inverse problem. And it's unstable as, it's usually unstable or ill-posed as inverse problems are, no matter how we formulate them. And since we usually have perturbed data, I just put here the noise level with respect to a quite general misfit functional S. We have to do something about this, so we have to regularize. So there are many ways of regularizing, and in particular, there are very straightforward in the context of problems that are already formulated as minimization problems, clearly because the probably most well-known regularization methods are already defined as minimization problems. So one can follow the idea, easily follow the idea of Tikhonov regularization and just add a regularization term, alpha times some regularization functional here to the cost function. One can also modify the admissible set. So you see it's modified here, not only in the sense that I've, of course, inserted the noisy data here because we just have the noisy data, but I also put a delta up here in order to indicate that we will possibly not only use the same admissible set with noisy data, but also modify this admissible set, for instance, by putting additional constraints. So putting constraints on the searched for quantity is also known to have a regularizing effect. This is the method of quasi-solutions, or in order to also put a name of a person, of a prominent person here, Ivanov regularization. These are basically the two approaches of doing regularization that lend themselves, of course, clearly in this context here as constraints, or I should say as penalty terms. And also one can distinguish different approaches in terms of how the noisy data are incorporated, or how the actually data misfit is incorporated. One can also add it as a penalty term in the cost function, as it's usually also done in the reduced setting, but one could also enter it into the game, so to say, via the admissible set. And this is clearly corresponding to the Morozov type choice of regularization parameters, or also to Morozov regularization, as it's sometimes called, which is actually regularizing by putting relaxed constraints on the data misfit. Okay, so let's get a bit more concrete about what this cost function J looks like. So, and this is referring back to the operators that define the model. So this A operator up here, and also the observations, the C operator. So for these observations, we want to kind of penalize the misfit to the data. And of course, we want to penalize in particular the misfit to the exact data, which means that we having some misfit functional S, it appeared already previously in the context of the noise level, we minimize this misfit term, and we simultaneously, with this additive penalty, minimize the misfit in the model. So we assume that we have some positive definite functionals, so they should also be non-negative, both of them, so that they don't interfere in any bad way. So both of them should be non-negative, and the value should be 0 if and only if these arguments are the same. So in this case, if the observations coincide with the measurements, and for the Q, we just want to achieve 0 here in the model. So Q should be 0 if and only if the argument is 0. So this is still formulating the inverse problem. So there are no constraints here. So we minimize over the whole space X times V. Now we go ahead and regularize this. And we first of all do so by adding a Tikhonov type regularization term to the cost function, and by redefining the admissible set in terms of such a constraint on another possible function, maybe a norm or something like this, also possibly on Q and on U. So this would be inserting Ivanov regularization. This is inserting Tikhonov regularization, and of course both can be done simultaneously. So the way in which the data misfit appears here is it appears as a term inside the cost function. So on the next slide, I will show you a version where appears inside the constraints, and therefore I call this approach here, in order to contrast between the two of them, regularization with data misfit penalization, RDMP. And so the next approach will be regularization by data misfit constraint. So it's a C instead of the P. So in meaning constraint here. So you see the change, maybe going back, the change between this slide and the next slide is that the S of C of U and Y has been moved into the set of constraints. Otherwise, everything is basically the same. And also here, it's basically S of C of U and Y equal to 0, which means, because of the definiteness of S, that C of U is equal to Y. So we would here ask the measurements to be satisfied exactly, which of course does not really make sense in case of noisy measurements. So this is kind of a theoretical formulation of the inverse problem, just in order to show that this regularization, where we relax the constraint, so maybe from the tau that appears here, you recognize Morozov's principle. Tau is this magic fixed parameter that we always use there. This is what one would do in practice, and this is just needed in order to prove that the thing below converges to the exact solution, as usual, as delta goes to 0. Okay, just very shortly about convergence. Let me look at the time. Okay, maybe a few minutes on convergence. So just to recall, the exact solution will be denoted by Q dagger and U dagger, just in order to have a notation for what things should converge to, and Y without any delta is the exact data. So what we assume on all these functionals appearing is, besides definiteness of S and Q, that was already on the previous slide, that these regularization functionals are proper convex functionals. Sorry, it's not written here, but clearly we also assume that the exact solution gives a finite value of the regularization function, and also that the exact solution is admissible for the regularized problem. So it satisfies the bound that is imposed by the Ivanov term. All the rest of this slide is kind of the usual assumptions on lower semi-continuity of all the mappings that are involved here, and a certain continuity assumption with respect to the data, basically, which is also somehow clear, since we want to have existence of minimizers, that we assume lower semi-continuity of the involved functionals. So it's also formulated quite generally. So as we know, at least since the seminal papers by Ottmar and his group, that it's actually enough to have some weaker topology that with respect to which we have this lower semi-continuity. So to get a bit more concrete, for instance, if R and R tilde are defined by norms, and so are S and Q, then it's clear that the tau will be typically the corresponding weak or weak star topology. So now just one slide about convergence. What we assume here is that the noise level in terms of this misfit functional here is bounded by some delta, and also in the Y norm, the noise tends to 0 as delta tends to 0. And then first of all, even without, of course, assuming this convergence to 0, it's clear from the previous assumptions that we get existence of a minimizer of the regularized problems. In both cases of data misfit penalization, and in case of this Morozov type thing, that we put the data misfit into the constraints. So this is about convergence, namely, it's, as you see, convergence about as delta tends to 0. So as delta tends to 0, we get convergence with respect to this tau topology or T topology. which we have used before in order to get well-definedness of minimizers. What we also need is clearly that the regularization parameters tend to 0 in an appropriate manner. Actually, if you put constraints, if you use Morozov regularization in some sense, we only need to use this part here, which just makes sure that alpha tends, that the approximation error tends to 0, because, so to say, Morozov regularization takes care of stability, whereas in Tikhonov regularization, of course, one has to do this more explicitly. This is the second condition. Okay, now about examples, and I would like to share with you this really nice example of electrical impedance tomography, which I really enjoyed reading. Actually, I would recommend this paper here, the McKenney paper, because there it's kind of described in a very intuitive way. And I would also like to mention there are many more papers on this topic, not only the 3 of them, but there are also papers on different applications. So this variational formulation, as it's called, they are applied in all kinds of inverse problems. And so what's it all about? So, well, I've shown you already, I mean, you know, of course, what the EIT problem is all about, but I would like to show you now a slightly different formulation. So not the one that is the second order elliptic PDE, where we have this conductivity sitting as a parameter inside, but so to say, going back to the physical modeling, at least a bit, and remembering that this second order elliptic PDE actually comes from the fact that we have Maxwell's equations in the back of our mind, in the sense that what we use here is that the divergence of the current density, capital Ji, is 0, and also that the curl, so this is the notation, the 2-dimensional notation for the curl here, that the curl of the electric field is 0 in the special setting that we have here, namely basically electrostatics. So these are the two, so to say, balance equations that we have. And here is, so to say, the material law, namely that the current is related to the electric field via the conductivity. And so what we observe here is boundary currents and voltages that can also easily be related to these quantities. Before doing so, what we see, actually what I have been teaching 3 weeks ago in my calculus course, is that if the curl of a vector field is 0 and the domain is simply connected, then there exists a scalar potential. And we put EI to minus the gradient of the scalar potential, like, for instance, the electrical engineers prefer to do. This is what is written here. And analogously, of course, there exists for a divergence-free vector field, there exists, well, in 3 space dimensions, it's a vector potential. In 2 space dimensions, it's again a scalar potential. And it's called psi here. So maybe at least at this point, I should say that this happens not only for one of these states, but for all of these states. So each excitation by some boundary current, we have, of course, a different electric field and corresponding electric current, or the other way around maybe, and also corresponding measurements of the voltages. So this is the I here corresponds to the numbering of the capital I different experiments that are made here. So now we rewrite these identities up here by just using these potentials, namely, and inserting into here. So using these potentials here, we write, as a consequence of this equation here, this Ji appearing here as minus the curl of psi I, and we write EI as minus the gradient of phi I. So the minus cancels out. So we have this relation with the sigma in between. And another thing that is done here, which is also nice because it gives advantages in the formulation of the minimization problem, is that we redistribute the factor sigma. So to say half of the factor goes to the left-hand side. So here it is. Goes to the other side with the square root, of course, in the denominator, and half of it remains here with the electric field. This is a kind of also nice formulation in the sense that it has a lot of symmetry in it. Well, and then we can have observations of both of them, and actually it's Dirichlet values in both cases, because we can transform these boundary currents into Dirichlet boundary conditions for the psi, because due to the curl here, they become tangential derivatives, so to say, and therefore we can just integrate along the boundary in order to get the Dirichlet boundary values for the psi. Okay, so this is still a formulation as a, well, kind of system of equations in the domain, equations on the boundary. It's first order with respect to derivatives as compared to the previous or first or second slide, second order formulation. And so what we do now, actually what they do, is just instead of this equality here, to consider, so to say, least squares problem, so to take the L2 norm of this, of the difference between the two sides here, squared L2 norm, and take this as a cost function. And then it's clear that this constraint minimization problem with, so to say, the model in the cost function and the observations in the constraints is an equivalent formulation of the electrical impedance tomography problem. So one of the nice things also comes here. If we compute the square here, then you see, because it's a complete square, so you see the square root of sigma and 1 over square root of sigma cancels out in the mixed term. And what also appears in the mixed term is that the gradient of phi meets the curl of psi. So they are orthogonal to each other in L2, clearly. Not completely, of course, up to a boundary term that emerges from integration by parts. But the boundary term then just contains, so to say, known quantities, namely known from the boundary conditions. And so what we end up with is this formulation, which is somehow a bit linear with respect to sigma. Let's put it like this. But it's, of course, a nonlinear, non-quadratic cost function, because you see it's sigma, phi, and psi that we want to use as design variables. And so you have a term that is quadratic in phi here and linear in sigma, so it's kind of cubic. And this one is not even cubic. But still, it's a kind of nice formulation here. So it's also quite straightforward now to regularize this. So of course, this is just a reformulation of the original, very ill-posed, as you know, inverse problem. To regularize it, we put constraints on the conductivity, which is also a natural thing to do, because quite often one knows maximal and minimal values of the conductivity. For instance, if one just has some material where two particular values of the conductivity are possible. So for instance, background material and some inclusion, then these values, if they are known, can be used as bounds here. And also the constraints are used in order to introduce Morozov regularization here. So instead of just imposing the measured data with equality here, we impose it with a margin of the order of delta here. So it's just up to a margin of plus minus tau delta that we impose this data on the boundary. So there's an additional term here, which does not look so nice. It's somehow artificial, and it is actually, it's really only needed in order to make sure that this problem is well posed, in the sense that there exists a minimizer, because, well, basically due to the fact that we have this non-linearity, so, and the fact that it's not non-linear, but also non-quadratic, we get that without this, such a kind or other kind of regularization, we would not be able to satisfy the lower semi-continuity property of the cost function. This is clearly a case where we have imposed the data misfit in the constraints, as you see here. So it's an RDMC case of regularization. Just to give you an idea on which function spaces are playing a role here. So clearly we need function spaces for the parameter, which is our sigma here. The state consists of all these states phi and psi, namely with indices small I going from 1 to capital I. So for all the experiments that we are doing, and Y collects all the data in one, so to say, data vector of boundary functions. We can use just L2 of omega as a space for the sigma. Nevertheless, sigma will be in L infinity, of course, because we impose a constraint. It's on its L infinity norm, basically. So we have this upper and lower bound on sigma, which of course renders it an infinity function if it satisfies this constraint. So the space Y here is not a Hilbert space, clearly. So this is, so to say, the minimal space that one would use here in terms of the data. But of course, one can still go to a higher order space, Sobolev space, to get also a Hilbert space setting. So for V, we again back with the Hilbert space setting. So it's just H1 functions. Additionally, since these H1 functions do not have sufficiently smooth traces by themselves, we also just put a bit of regularity of these traces into the definition of the space. For the W space, we can again use L2. And then just to, so to say, satisfy the formalities, this would then be the model operator, and the observation operator would just be the trace on the boundary, namely the traces of all these state functions. So it's trace operator to the 2i. Now, time is finished in 2 minutes, isn't it? Sorry.
I think you can, I think you at least 7 minutes. I mean, if you want to have 10 minutes discussion, then maybe 7 minutes would be good.
Yes, okay, so thank you. So let's stop about these formalities. So of course one can prove convergence, and maybe let's stay a bit with these remarks. So first of all, I was insisting on these Hilbert spaces for a good reason, at least in my view, namely the fact that if you think of iterative minimization methods, for instance, gradient methods, it's in Banach spaces, it's sometimes really tedious to define and implement them. Just due to the fact is that if one is in Banach spaces, then first of all, the gradient maps to the dual space. Then you have to find a way to come back from the dual space to the original space. And so it quite often adds non-linearity to the problem, and it also adds non-differentiability to the problem. Or I can add this. And also the choice of the step size is sometimes a bit of a headache. So this is why I was kind of insisting on these Hilbert spaces. Well, I mentioned non-differentiability already, or non-smoothness. The cost function that appears here is also nice and differentiable with respect to all variables. About the constraints, there are particular cases of constraints, namely linear constraints, and even more particular, they are pointwise bounds. So they are, so to say, in the discretized settings, they are box constraints, and such constraints can be very efficiently implemented. And well, what I also wanted to mention is that the formulation that I've shown you is a first order PDE, not actually PDE, but least squares formulation of the PDE model. So looking at the Euler-Lagrange equation, so first order necessary optimality conditions without taking into account the equality constraints, leads back to clearly a second order model, namely as it should be the second order model that we are used to in EIT. What is also nice here is one can incorporate the complete electrode model. This is what I have done together with my PhD student, Kar, recently, or what we're about to do, hopefully, we have submitted it already. And then it leads to a finite dimensional image space. And on finite dimensional image spaces, one can do something in addition because, well, if the observation operator has a finite dimensional image space, then it's, so to say, by definition, invertible. So one can find, or at least it has a right inverse and even a bounded right inverse, because finite dimensional spaces are always closed, and so operators on finite dimensional space, the ranges of operators on finite dimensional spaces are closed if these operators are continuous, and this also leads to some nice extensions of methodology, which I'm not going to get into detail here. So I think, I'm afraid I will completely skip these nice pictures about sound source identification, because it would be going through the whole model. It's actually to some extent analogous to the EIT problem. You see it ends also with a convergence corollary, and with this set of remarks. I even have computational results, actually really nice computational results that have been obtained by Manfred and Stefan in a 3D setting. But maybe let's just have a look, to be more honest, on experiments that I've done myself. And they are clearly not for such a advanced model. I've called it model problem, to be more honest. It's maybe just a toy problem. It's first of all on the unit square, and it's with interior observations. So it's the well-known C problem. So identifying this coefficient C here in the zero order term of the elliptic PDE that you have seen on one of the very first slides. And but what I wanted to show you here is that well, this would be the minimization-based formulations, also some kind of least squares formulation in an appropriate space. So the elliptic operator here is considered as an operator mapping from H01 to H-1. And so in some sense, this is also something like a first order PE formulation, but not quite, of course. And we put this Morozov type regularization as a constraint on the data misfit. Now, what I would like to show you at the very end is that not only we can recover, so to say, inclusions of the potential for positive values, but also for values with different signs here, and also for negative values where this PDE is clearly not elliptic anymore, and so the parameter to state map is not well defined. We do so by using this approach, implementing these box constraints both on the data misfit and on the coefficient itself, by also a very nice method that has been devised by two of my colleagues, namely Franz Reindl and Philipp Hungerländer. So this is the background about discretization. Here we do piecewise linear discretization for the state, piecewise constant for the coefficient, and we have to linearize, or actually we have to render the nonlinear cost function quadratic, and we do so by a Gauss-Newton method. So this is about stopping and about the magic constant tau in here. So maybe let's proceed to the last test, because I'm trying, I wanted to try to impress you by this, namely the test, or the next to last, yes, the last test, where both of them are negative, and clearly there's no chance to get any result with the reduced approach, because it's just not possible to solve the PDE because it's not elliptic. So these are the points where, so we, just to recall, we do observations, of course, in the whole domain, but these are the points where we check convergence, so to say. So it's just weak star L infinity convergence of the coefficient C that our convergence results predict. And we can, of course, we need, so weak star L infinity means in the dual of L1. And so these, the characteristic functions of these three spots here, or actually of these three very small patches here, are the L1 functions with which we test here. And so this is, it's actually an active set method. So it detects the set where the upper bound on C and the lower bound on C is active. And so you see here with 1% noise, the K is the number of Newton steps that we use here. Of course, at the beginning, it's not able yet to determine the active set. It is nevertheless able to determine a crude approximation of the coefficient C, as you see here. And as the iteration proceeds, it determines the active set of the lower bound of this coefficient. So clearly the lower bound, because it's minus, it's deeply in the minus, so the lower bounds are important here. The second inclusion here is at no bound at all, so we cannot expect that it's detected here because it has a negative, but in absolute value smaller negative value. Still, it's detected here in the reconstruction. And well, here you see the active set for the upper bound, which is basically the region in which the background material is. So it does weird things here, of course. It, in some sense, sees that we are not active in this part, and also we are not active in this part where the second inclusion sits, which makes sense, of course, but for the rest, it does not detect the active set properly. Nevertheless, it's able to very nicely reconstruct this negative coefficient. And with this, I would like to thank you for your attention and stop the presentation.
Thank you very much, Barbara. This was a really, really interesting presentation. Thank you. And I'm very happy to say you lost about 5% of the participants, so extremely little, nice. Which I'm sure left for good reasons. So any questions? Yes, Yuri has a question. So let me see who can actually unmute Yuri. Fadil, can you unmute? Talking permitted. Okay. Okay, Yuri, you can speak.
Yeah, Barbara, thank you very much for your very interesting talk. I was wondering, you assume that the noise in your measurement Y is in L infinity, so that you have an L infinity pointwise bound on the measurement noise. What is the reason for this, and how realistic is it?
Well, the reason for this is first of all, I think in some applications it makes a lot of sense to just have a L infinity bounds, because quite often in my far past, escape to the L2 norm was just in order to use Hilbert spaces, to be honest, where noise is actually in, where we had, especially we had deterministic noise, and this was typically rather in L infinity than in L2. So this was part of my motivation. And the other part of the motivation is that with this L infinity noise, the the misfit in the misfit constraint just becomes a box constraint. So let me try to get to the slide where I can show it, or to one of the slides where I can show this to you. So maybe here. Okay, no, it's not here. Maybe it's better. Oh, it's better to. Not sure whether it's better here. Yes, but well, maybe let's look at this. So S is the L infinity norm here, yes? And so bounding the L infinity norm, the difference between the L infinity difference between C of U and Y delta by some bound is equivalent to putting Y delta minus tau delta as a lower bound pointwise almost everywhere in the domain, and putting Y delta plus tau delta as an upper bound pointwise everywhere. Maybe it's better visible in the EIT slide.
Okay, is that okay, Yuri?
Yeah, thank you.
Okay, great.
Thank you.
So just before Christian asked his question, just to say that there are lots of compliments coming in for your talk, Barbara. So you really gave a great talk.
Thank you. That's
yeah.
nice. Mm-hmm.
Christian.
Yeah. Hi, Barbara. Thank you for the talk. Very nice.
Mm-hmm.
I have some questions about the regularization term you were using. I know Tikhonov is kind of outmoded these days, but you were using a coupled, or well, a parameter state regularization term. And I was wondering about the regularization of the state specifically. So you showed for the EIT an example, but I was wondering whether in general you can use the same degree of freedom which you use for the parameters, where you use some sort of structural properties to play with the regularization terms to find better ones, maybe Banach space ones, and whether something like this is also sensible for the state.
Yes, I think it could be, because if we want to have states that are well, not the states themselves will have jumps, but typically actually in the AIT example, I would expect that the gradients of the states will have jumps, isn't it? It's related to the jumps in the sigma. And this could also be reflected in a more sophisticated regularization term here.
True. You could probably also do spatially dependent regularization terms.
Yes.
You know, better control of the state at some
point. Yes, that's right. Yes.
Kalman weight functions. Thank you.
Thank you.
Okay, thank you. Are there more questions? Yes, Thomas has a question. Thomas Schuster, okay, you are permitted to talk, Thomas.
Yes, thank you, and thanks, Barbara, for the nice talk. And it's
nice to see
and to hear all of you. And I hope you are all healthy and that we can meet again personally at some time.
Yes,
well,
we can, hopefully.
I have a question about this comparison between your all-at-once setting compared to the reduced setting. You told that the all-at-once setting is more efficient from a numerical point of view because you do not have
Okay, you're breaking up, Thomas.
Okay, so can you hear me right now?
Yes, you said it's more efficient because?
Okay, you said it's more efficient because you have less parameter state evaluations in iterative methods, for example. But now you have two unknowns, Q and the solution U. So you have a higher dimensional problem. So is it really more efficient than the reduced model? Can you tell something?
Yes, I can say something. Sorry, I didn't want to claim that it's always more efficient. Of course, there's this aspect of larger systems versus the aspect of being able to reduce, as the name also says, the size of the system, just to split the thing into separately solving the PDE problem and evaluating the observation operator. But well, we have done some comparisons for problems that are nonlinear, and if the stronger nonlinear the problems are, the more it pays off to do these simultaneous things here. Of course, even if one is in this setting of so down here of simultaneous equations, one can also still iterate between the two of them. Yes, it's not necessary that one really has to solve the large system altogether. And also, what I would like to mention, the growth in size is usually also not so much, because the main load, so to say, is the PDE problem. And what we add here is just the observation equation, which is usually just on the boundary, so in a lower dimensional space, so to say. But yes, it's mainly about nonlinear problems. So for nonlinear problems, it really pays off. For linear problems, not necessarily.
Okay, thanks a lot and stay healthy.
Thank you. You too.
Thank you. So, Barbara, one last question is coming through the chat from Bohan Ju. And the question is, so first of all, thanks for the nice talk. Could you explain the comparison between the different norms for error and the comparison between the norms for restrictions or regularizations, like for computational aspects, convergence aspects, etc.?
Yes, thank you for this question. Of course, the choice of norms is very important. So let's maybe move back to this sort of simplistic slide here. Of course, it makes a large difference which norms we take here in order to measure the data misfit and the model misfit. So in the example that I showed, and actually also in the example that I wanted to show, I wanted also to stress somehow that for instance, the norm in the model misfit is kind of natural. It comes natural with this first order system formulation of the EIT problem and also later on of the acoustics problem. So avoiding too high norms of the states, because as you know, the higher the regularity of the state is, the more ill-posed the problem is, and we don't want to make it ill-posed artificially. So if you impose low order norms here in our formulations, then this could also help to make the problem maybe slightly less ill-posed. Of course, it's not makes no difference at all for severely ill-posed problems, but it might make a difference for moderately ill-posed problems, where really the choice of the norms makes an impact on the, or a visible impact on the degree of ill-posedness. So, well, the norm, maybe to just also say something on this norm here. This norm is more or less imposed by the, so to say, the topology in which we can measure the data, in which we can more precisely assess the data noise. So here we are, so there is also usually some kind of natural way of choosing this norm, or more generally the data misfit here, when I denoted this by S, by just taking into account, for instance, the statistical distribution of the noise and things like this. Does this answer your question?
I think it does, but yeah. So thank you so much again, Barbara. This was really, really great. It was a great talk. And yeah, I mean, I guess I second Thomas. Please all stay healthy. Join us again next week for another session. And yeah, a round of applause again for Barbara. So thanks Thanks a lot. Thank you very much.
Thanks to you for coming.
Thank you. Bye bye, everyone.
Bye.
Bye.
Bye. Bye.
Bye.